The universe is an unfathomably vast expanse, teeming with an astonishing array of celestial wonders. From minuscule rocky fragments to colossal galaxy clusters, the cosmic abyss holds countless marvels. Today, we embark on an extraordinary voyage to the farthest reaches of the visible universe. Our journey starts at the heart of the magnificent Milky Way, where we'll explore its radiant core, veiled dust clouds, and glittering star clusters. From there, we'll venture into its enigmatic halo, a region shrouded in mystery. Next, we'll traverse the cold, perilous realms of intergalactic space, saturated with dangerous radiation. This leg of the journey will lead us to some of the most extraordinary galaxies scattered throughout the vast void of deep space. Spanning billions of light years, we will dive into the enigmatic depths of immense cosmic voids and push toward the outermost edges of the metagalaxy. This incredible odyssey will not only grant us a glimpse into the ancient past of our universe, but may even offer insights that extend beyond its known boundaries. Let's prepare for an awe-inspiring adventure as we begin our exploration of the cosmos. Long before telescopes, humanity gazed at a luminous band stretching across the sky, sparking myths and legends. This mysterious phenomenon, later identified as the Milky Way, is the combined light of billions of distant stars, too remote to distinguish individually. In 1755, philosopher Immanuel Kant proposed that the Milky Way was a vast structure of stars, suggesting that certain nebulae might be other galaxies. Though initially dismissed, his theory gained traction in the 20th century with advancements in observation technology. By 1936, Edwin Hubble introduced a classification system, placing the Milky Way in the category of barred spiral galaxies. The Milky Way spans an impressive 200,000 light-years in diameter, with a halo extending even further. It contains at least 200 billion stars, 25 to 100 billion brown dwarfs, and over a trillion planets. Despite this abundance, regular matter accounts for only about 10% of the galaxy's total mass. The remaining 90% is dark matter, an enigmatic substance detectable only through its gravitational effects. The Milky Way's estimated mass is between 800 billion and 1.5 trillion solar masses, calculated from the orbital movements of its stars. At the galaxy's center lies a supermassive black hole named Sagittarius A*, surrounded by a dense accretion disk spanning 3 light-years. With a mass of 4.3 million suns, its gravitational pull shapes the surrounding stars and matter. The central region teems with activity. More than 6,000 stars lie within 3 light-years of the black hole, including the star S62, which orbits at 6.7% of the speed of light. This area also hosts molecular clouds filled with dense hydrogen, carbon monoxide, and other compounds, along with stellar nurseries where new stars are born. Encasing this active core is the bulge, an elongated, elliptical region 10,000 light-years long and 7,000 light-years wide. The bulge contains billions of ancient stars and forms the foundation for the galaxy's iconic spiral arms. The Milky Way's spiral arms, such as the Perseus and Scutum Centaurus arms, are rich in young stars, interstellar gas, and dust. These regions are stellar nurseries where stars form 3 to 5 times more frequently than elsewhere. The solar system resides in a minor arm known as the Orion Arm, about 27,000 light-years from the galactic center. This area falls within the galactic habitable zone, a ring-shaped region with conditions most suitable for the development of life. However, the position of stars within this zone can shift due to migration over billions of years. The galactic disk consists of 2 components. The thin disk, about 1,000 to 1,300 light-years thick and containing 80% of the galaxy's visible mass. The thick disk, 4 times thicker but more diffuse, primarily composed of older stars. These components suggest a tumultuous history, including a merger with a smaller galaxy dubbed Giant Enceladus 8 to 11 billion years ago, which contributed stars, gas, and dark matter to the Milky Way. Surrounding the galaxy is the halo, a vast, diffuse region extending up to 260,000 light-years. It contains ancient stars, globular clusters, and streams of stars stripped from smaller galaxies. For instance, the Sagittarius dwarf galaxy is currently being absorbed by the Milky Way. Beyond the visible halo lies the dark halo, a sphere of dark matter stretching up to 2 million light-years. Though invisible, its gravitational influence ensures the galaxy's stability. The Milky Way, a complex and dynamic structure, continues to intrigue scientists as they unravel its mysteries. From its bustling core to the enigmatic dark halo, our galaxy offers endless opportunities for exploration and discovery. Intergalactic space refers to the vast regions of space between galaxies, often thought to be nearly empty and close to an absolute vacuum in composition. These regions, which can stretch millions of light-years, are primarily filled with ionized gas, mainly hot hydrogen with a density less than 1 atom per cubic decimeter, significantly lower than interstellar environments. Heavier elements like carbon, oxygen, and silicon are also present. Some intergalactic gas forms diverse clouds varying in density and temperature, containing elements such as hydrogen, helium, nitrogen, sulfur, and various metals. This gas is vital for star formation within galaxies, serving as a raw material. Intergalactic space also hosts larger objects, such as rogue stars, with their total number in the observable universe estimated in the trillions. Within the Milky Way alone, around 650 such stars have been identified. Most intergalactic matter is invisible, as it emits little to no light, and its discovery in the 1960s came by chance through observations of quasars. The presence of missing spectral lines in quasar light led to the identification of the intergalactic medium, IgM, comprising vast accumulations and filaments of gas and heavier elements. Despite its seemingly sparse nature, the total amount of intergalactic matter likely exceeds the combined mass of all galaxies in the observable universe. This matter plays a critical role in the universe's evolution, with gas being drawn into galaxies at rates matching star formation, allowing for the continuous recycling of matter through processes such as stellar winds, supernovae, and gravitational interactions. Distances from the Milky Way to other galaxies are, by any standard, utterly mind-boggling. Typically, these distances range from millions to billions of light-years. This vast separation is exacerbated by the universe's cosmological expansion, which continuously increases the distance between Earth and any remote cosmic object. This expansion causes the light emitted from distant objects to stretch, making it appear redder than it originally was. This phenomenon, known as redshift, serves as a vital tool for astronomers to measure distances and velocities on an astronomical scale. On the other hand, certain galaxies exhibit a blue shift in their spectrum, indicating they are not receding from us but are instead moving toward the Milky Way. One of the most intriguing of these is the galaxy M86. M86, the galactic predator. M86 resides in the Virgo cluster, approximately 52 million light-years away from the Sun. Unlike most galaxies, it is moving toward the Milky Way at an astounding velocity of 244 kilometers per second, making it one of the fastest-moving blue-shifted galaxies known. As it hurtles through the thin gas of the Virgo cluster, M86 sheds its interstellar matter, creating an extraordinary trail of ionized hydrogen stretching across space. This trail, formed by the stripping process, hints at the dynamic interactions the galaxy experiences. Interestingly, M86 is gravitationally linked to the spiral galaxy NGC 4438. This connection is marked by several filamentary structures between the two, evidence of a past collision. This cosmic encounter significantly altered NGC 4438, leaving it almost entirely destroyed. M86's destructive legacy doesn't stop there. Observations reveal that it has consumed multiple neighboring galaxies in the past, leaving behind stellar streams in its halo as remnants of these smaller, devoured galaxies. Adding to its intrigue, M86 boasts an extraordinary number of globular clusters, over 3,800, approximately 25 times the count found in the Milky Way. These clusters may well be remnants of dwarf galaxies previously absorbed, suggesting that M86 has obliterated tens, possibly hundreds, of galaxies over its tumultuous history. ESO 137-001, the galactic jellyfish. Another fascinating galaxy, ESO 137-001, resides some 227 million light-years away, within the massive galaxy cluster Able 3627. Weighing between 5 and 14 billion solar masses, this galaxy predominantly contains young, bright blue giant stars. ESO 137-001 is remarkable for its rapid movement, traveling toward the cluster's center at nearly 2,000 kilometers per second. This high velocity causes it to collide with intergalactic gas, resulting in a dramatic stripping of its own gas and leaving behind luminous tails that extend up to 260,000 light-years. These tails are composed of hydrogen gas that is 2 to 4 times more massive than the gas within the galaxy itself. These gaseous tails are sites of intense star formation, known as starbursts, producing countless young stars. Observing ESO 137-001 from the side reveals a structure reminiscent of a colossal jellyfish, with its gaseous trails resembling tentacles floating in the vastness of space. However, this gas loss comes at a cost. As its reserves are depleted, the galaxy's ability to form new stars diminishes, shortening its lifespan. This slow death significantly impacts the structure of ESO 137-001's spiral arms and central bulge. Despite this grim future, the galaxy offers scientists a unique opportunity to study the interplay between dark matter and interstellar gas. The Baby Boom Galaxy, a stellar nursery. Located an astounding 12.2 billion light-years from Earth, the Baby Boom Galaxy earns its name by being a veritable star factory. In this extraordinary galaxy, approximately 4,000 new stars are born each year, a rate nearly 400 times that of the Milky Way. This means a new star ignites in the Baby Boom Galaxy roughly every 2 hours. Observing this galaxy provides a glimpse into the universe's infancy, as its light reflects events that occurred just 1.5 billion years after the Big Bang. The reasons behind such prolific star formation remain a mystery. However, the Baby Boom Galaxy is a treasure trove of information about the early universe's evolution, shedding light on how galaxies and stars formed during a period when the universe was still shaping its fundamental structures. The Sombrero Galaxy, a cosmic hat. One of the few galaxies visible through small telescopes, the Sombrero Galaxy, officially designated M104, lies 30 million light-years away. With a diameter roughly 4 times smaller than the Milky Way, its most striking feature is a prominent ring of dust and cold hydrogen gas encircling its core. This ring is the primary site of active star formation, hosting clusters of young stars. Beneath this dust ring lies an intricate inner structure. Observations with the Spitzer Space Telescope reveal that most of the galaxy's stars form an elliptical shape, consisting mainly of older, red and yellow stars. Meanwhile, the younger stars contribute to a spiral structure, creating a fascinating blend of galactic features. This unusual combination is likely the result of a past collision between 2 galaxies, whose stars merged to form the present structure. At its core, the Sombrero Galaxy harbors an exceptionally massive black hole, with an estimated mass exceeding 1 billion solar masses. This black hole is among the most massive known, contributing to intense X-ray radiation and other high-frequency emissions detected within the galaxy. These enigmatic emissions continue to intrigue scientists, offering clues to the mysteries of galactic evolution. M64, the Black Eye Galaxy. Lastly, the enigmatic M64, also known as the Black Eye Galaxy, earns its name from a dark band of cosmic dust that partially obscures its bright nucleus. Situated approximately 17 million light-years from Earth with a radius of 25,000 light-years, M64 is a relatively small galaxy with a highly unusual structure. The galaxy is composed of 2 distinct parts, an inner disk that rotates in the opposite direction to its outer ring. This bizarre arrangement likely resulted from a collision between 2 smaller galaxies in the distant past. Such a merger would have required an extraordinarily specific set of conditions, including precise velocities and collision angles, to produce the well-defined and stable structure observed today. M64's striking contrast of opposing rotations creates dynamic interactions that influence its evolution. While the exact number of stars in the galaxy remains uncertain due to the obscuring dust, its bright nucleus and unusual rotational dynamics continue to captivate astronomers. Our planet, Earth, is but a minuscule fragment in the grand cosmos, a tiny rocky sphere orbiting a medium-sized star within a galaxy of billions. Earth maintains an average distance of approximately 150 million kilometers from the Sun, a fact that underscores our fragile place within the vast solar system. Yet, even the Sun's domain is dwarfed by the enormity of the cosmic structures beyond. According to contemporary astronomical concepts, the outer boundary of our solar system extends to the hypothetical Oort cloud, located about 100,000 astronomical units away. Beyond this lies an immense interstellar vacuum, a region so sparse that it contains, on average, only one hydrogen atom per cubic centimeter. To appreciate the scale of the universe, let's begin with our closest neighbors. The distances between stars in the Milky Way are often measured in light years, a light year being the distance light travels in 1 year, about 9.46 trillion kilometers. The nearest star system, Proxima Centauri, lies over 4.24 light-years away. Imagine a photon leaving the Sun. It could travel to Proxima Centauri without colliding with any matter. This unfathomable emptiness forms the vast voids separating stars, planets, and other celestial objects. Void regions, also known as cosmic voids, are vast expanses of nearly empty space between galaxies and galaxy clusters. These voids are essential components of the universe's large-scale structure. They form an intricate network with galactic filaments, creating what is often described as the cosmic web. The voids are characterized by low densities of matter compared to the surrounding areas. One such example is the local void, a massive region near our Milky Way galaxy. Spanning roughly 150 million light-years in diameter, the local void is slowly expanding due to the cosmological expansion of the universe. Its nearest edge lies about 3.2 million light-years from Earth, occupying approximately 40% of our night sky. Remarkably, one of the galaxies within this void, NGC 6503, displays a stunning multicolored appearance with spiral arms filled with bright red hydrogen regions and glowing blue nebulae. This galaxy, about 17 million light-years away, is gradually moving toward the Virgo supercluster at a speed of 43 kilometers per second. The origins of voids trace back to the universe's infancy during the chaotic moments after the Big Bang. Intense gravitational interactions and energy fluctuations caused matter to clump together in some areas, forming protogalactic clouds, while other regions remained sparsely populated, becoming voids. Over billions of years, gravity accentuated these contrasts, pulling matter into dense clusters and making voids even emptier. Interestingly, galaxies and voids are not vastly different in age from those in denser regions, supporting the theory that voids and galaxies formed simultaneously. However, void galaxies tend to be isolated and exhibit slower rates of star formation due to the scarcity of intergalactic gas. For example, UGC 2627, a spiral galaxy, resides deep within the Taurus void, nearly 185 million light-years away. This isolation fosters unique evolutionary paths for such galaxies. In 2013, astronomers led by Amy J. Barger and her colleagues discovered the KBC void, the largest supervoid known to date. Spanning an estimated 2 billion light-years in diameter, this void envelopes the Laniakea supercluster, which includes our own Virgo supercluster and the Milky Way. The KBC void's existence helps explain anomalies in the measurement of the Hubble constant, a value that describes the rate of the universe's expansion. Galaxies within the void, including our own, experience gravitational pulls from denser regions outside, causing peculiar velocity shifts. Galactic superclusters, such as the Virgo supercluster, are massive conglomerates of galaxies bound by gravity. The Virgo supercluster spans 200 million light-years and contains about 30,000 galaxies. It is part of the larger Laniakea supercluster, which encompasses over 100,000 galaxies and stretches 500 million light-years. Laniakea's gravitational center, the Great Attractor, lies 250 million light-years from Earth and significantly influences the motion of galaxies within this region. The CMB cold spot, located 6 to 10 billion light-years away, represents one of the most intriguing voids in the universe. Measuring up to 1 billion light-years in diameter, this void significantly impacts the cosmic microwave background radiation, the afterglow of the Big Bang. Scientists speculate that its peculiar properties might hint at exotic phenomena, such as dark matter concentrations or remnants of quantum fluctuations from the early universe. As the universe continues to expand, voids are expected to grow larger and more rarefied. The Virgo supercluster may eventually disintegrate into smaller, independent groups. Meanwhile, neighboring voids like the Local Void and Taurus Void might merge into even larger regions of emptiness. Some theories suggest voids could harbor exotic forms of matter, such as dark matter or negative mass. Though these ideas remain speculative, they challenge our understanding of the universe and push the boundaries of astrophysical research. Cosmic voids are among the most fascinating yet least understood structures in the universe. They provide a window into the forces that shaped the cosmos, from the Big Bang to the present day. These immense regions of emptiness are not just gaps in the universe, but are integral to its vast architecture, separating galaxies, superclusters, and the cosmic web itself. As our observational technologies improve, the study of voids will undoubtedly continue to reveal profound insights about the nature of the universe and our place within it. The solar system is but one of countless planetary systems scattered across our galaxy. It consists of a single main sequence star, 8 planets with their moons, and over 1 million small celestial bodies such as asteroids, comets, and meteoroids. Neptune, the farthest known planet in the solar system, orbits at a distance of approximately 30 astronomical units, roughly 4 light-hours from the Sun. Beyond Neptune lies the remote, far out, an object discovered at 132 astronomical units, or 18 light-hours away. However, even this is not close to the hypothesized Oort cloud, whose inner boundary is estimated to be around 2,000 astronomical units, and whose outer boundary may extend up to 60,000 astronomical units, about 1 light-year. These limits mark the extent of the Sun's gravitational influence. Beyond them lies interstellar space. Within 20 light-years of the Sun, over 50 stars of various types are found, ranging from dim brown dwarfs to brilliant stars like Sirius and Procyon. Many of these stars have planetary systems, some with potentially habitable worlds. One example is Gliese 832c, an exoplanet located 16.1 light-years away. It has an average surface temperature of approximately 253 K, minus 20 degrees Celsius, and completes an orbit around its parent star in just 36 Earth days. Despite being relatively close by astronomical standards, a spacecraft traveling at 17 kilometers per second would take roughly 300,000 years to reach it, emphasizing the vast distances involved. The solar system resides in the Orion arm of the Milky Way, a galaxy containing around 400 billion stars and potentially over 1 trillion exoplanets. The galaxy spans about 100,000 light-years in diameter, with a central bulge approximately 3,000 light-years thick. Surrounding the Milky Way is a stellar halo that may be twice as wide as the main disk. The Milky Way, along with the Andromeda Galaxy and the Triangulum Galaxy, forms the Local Group, a cluster of over 50 galaxies spanning 10 million light-years. Together, these galaxies account for a significant portion of the cluster's estimated 3 trillion solar masses. The Local Group is part of the Virgo supercluster, which contains over 30,000 galaxies within a region approximately 150 million light-years in diameter. This supercluster, with a mass equivalent to a quadrillion suns, is relatively flat, resembling a sheet about 10 million light-years thick. Expanding further outward, the Virgo supercluster is part of the larger Laniakea supercluster, which encompasses several galaxy superclusters, including the Great Attractor. Spanning 520 million light-years, Laniakea has a mass of around 100 quadrillion suns and influences the movement of galaxies within its domain. Beyond superclusters lies the large-scale structure of the universe, comprising filaments, walls, and voids. Among these is the Hercules Corona Borealis Great Wall, a structure stretching an astonishing 10 billion light-years. This immense formation is home to countless galaxies, Yet its existence challenges current cosmological theories, which suggest that such massive structures should not form in the universe's timeline. The observable universe is a sphere with a diameter of about 93 billion light-years. Its boundaries are defined by the limits of what light has reached us since the universe's inception. Beyond this lies the unobservable universe, which may contain structures and phenomena entirely beyond our comprehension. Hypothetical regions beyond the observable universe, often referred to as extra-metagalactic objects, remain a mystery. Movements of distant celestial objects suggest the presence of massive unseen structures exerting gravitational influence. These anomalies hint at a universe beyond what we can currently detect, raising questions about its nature and scale. Some theories propose that the observable universe is just one part of a much larger multiverse. According to these hypotheses, other bubbles of existence may have entirely different physical laws. Radical ideas even suggest that our universe might be a simulation, controlled by advanced civilizations whose goals and capabilities are beyond human understanding. The vastness of the universe, from the solar system to the largest known structures, challenges the limits of human imagination. As technology advances, we may uncover more about these mysteries, but the universe's ultimate boundaries, whether physical, conceptual, or metaphysical, remain elusive. For now, our understanding is but a small glimpse into the infinite complexities of the cosmos. In conclusion, the universe, as we currently understand it, is a vast and awe-inspiring construct filled with mysteries and unimaginable scales of distance, mass, and complexity. From the solar system to the edges of the observable universe, each layer reveals new insights and challenges our understanding of reality. While scientific advancements have unraveled much about our cosmic surroundings, the boundaries of the universe remain elusive, hinting at structures and phenomena beyond human comprehension. These mysteries, coupled with the tantalizing possibility of multiverses or alternative realities, undo the limits of our knowledge and fuel our quest for discovery. As we continue to explore and theorize, the universe serves as a reminder of both our insignificance and our unique role as observers in this grand cosmic tapestry.